Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so this question asks to draw the Lewis structure for the sulfur dioxide molecule. Be sure to include all resonance structures and that they satisfy the octet rule. You just okay. So the SO2 molecule, when we write the Lewis structure, we need to first find out the total valence electrons in the molecule. In the case of sulfur, there are 6 valence electrons. And in the case of oxygen, there are also 6 valence electrons. And since we have 2 oxygen atoms, there are 12. And then if we add them all up, then we get a total of 18 valence electrons. So we start off by writing the central atom, which is sulfur, and then we write the 2 terminal atoms on either side. So I'll just draw the oxygens on either side. And also recall that every bond contains 2 electrons that take part in the bonding. So far I've only drawn 4 valence electrons, and now I'm going to fill out the rest on as lone pairs on our terminal atoms. But before I finish writing out the oxygens, you'll notice that our sulfur doesn't have a full valence shell. So I'm going to draw a double bond. And let's count out to see how many electrons I've drawn so far. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I just need 2 more. And I'm going to put them on the sulfur, since sulfur doesn't have a valence octet or a full octet yet. And after doing that, it now has a positive charge. And this oxygen on the left has a negative charge. So this is one Lewis structure of SO2. And if we were to draw the resonance, another resonance structure of this molecule as well, we'll show this oxygen having the double bond instead, and the oxygen on the right to be single bonded. So again, it's just the same concept, but the oxygens have switched sides. Okay, so these are 2 resonance structures that satisfy the octet rule. So the junior tutor said to first determine the total number of valence electrons. The sulfur atom in group 16 has 6 valence electrons, and the oxygen atoms in group 16 have 6 valence electrons as well. for a total of 18 valence electrons. Second is to draw a plausible skeletal structure by joining atoms through single covalent bonds. Third, subtract 2 electrons for each bond in the skeletal structure. The 2 bonds in this structure account for 4 of the 18 valence electrons. This leaves 14 valence electrons to be assigned. Next is to complete the octets for the terminal oxygen atoms and assign the remaining valence electrons to the central sulfur atom. Okay, so they added all the lone pairs and noticed that the central sulfur atom does not have a complete octet yet. So we assign multiple bonds between the sulfur and oxygen, forming 2 resonance structures. Yep, so this solution is correct. Not sure if the question asked to add formal charges, but yeah, I'll just add that for the resonance structures, the sulfur atom will have a positive charge and the oxygen, or the single bonded oxygen, will have a negative charge. Okay, so question number 2 is also a Lewis structure question. The following Lewis structures for hydrogen cyanide, ethylene, tin oxide, and boron trifluoride, and so on, are incorrect. Explain what is wrong with each one, and give a correct structure for the molecules. This is an interesting take on the Lewis structure questions. So let's start off with writing the wrong molecule, just so that we can compare it and see what's wrong. So it's supposed to be a molecule of HCN. So let's start off with writing all the total valence electrons in the molecule. So hydrogen has a valence electron of 1, carbon is 4, and nitrogen is 5. So if we add it all together, we're only supposed to have 10 valence electrons in this molecule. So if we count it out with each bond containing 2 of them, we have 6 in the form of bonds, 7, 8, 9, 10, 11, 12. So this molecule has 12 electrons. So if we were to draw the correct version, this lone pair of carbon, I'll turn it into a bond. And the nitrogen should only have 1 lone pair. So you'll notice that the carbon still has a full octet, and you'll notice that the nitrogen now just has a single lone pair. So if we count out the total valence electrons, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is the correct structure. Okay, so now let's check out what's wrong with the next molecule. Okay, so already looking at it, each hydrogen has a double bond. So I'll just say hydrogen shouldn't have a double bonds. This is because it only has 1 electron available to share, So you'll never see hydrogen having a double bond. So now let's try to find out how many electrons are supposed to be in this molecule. We have 2 carbon atoms, each with 4 valence electrons each, and we have hydrogen with 1 electron each, but there are 2 of them as well. So we're only supposed to have 10 electrons in this molecule. And the one on the left also has more than enough, so it has like around 12. So let's draw the correct structure with single bonded hydrogens. The carbon will still have a double bond, or actually it should have a triple bond now, so that it would have a full octet. And then the last carbon also has a single bonded hydrogen. So if we count out all the electrons, there are 10. So this structure is now correct. Okay, so the next one, we have 2 single bonded oxygens to tin. And now let's count out how many valence electrons are supposed to be in this molecule. So tin has 4 valence electrons. For oxygens, it'll be 6 times 2. So that leaves us with 12, 13, 14, 15, 16. So we need 16. And if we look at the incorrect molecule, you'll notice that tin doesn't have a full octet. So I'll say SN doesn't have a full octet. And if we count out all the electrons in this molecule, there are only 12 when we need 16. So let's try to write the correct one on the right. For tin to have a full valence, to have full octet, I'll draw these oxygens as double bonds instead, and then just write down the remaining lone pairs. Yeah, and in the old molecule, both of them don't have a full octet, so that's why extra. And now if we count out all the electrons in this molecule, you'll see that it is now 1, 2, 3, 4, 5, 6, 7, 8, 16. Okay, so let's start a new page and go to the next molecule. We have boron that is attached with 3 fluorine atoms, and it also has a lone pair. So let's calculate how many valence electrons are supposed to be in BF3. So for boron has 3 valence electrons, and for a fluorine atom, it has 7. And there's 3 of them, so 21 plus 3 is 24. So if we count out how many electrons are in this molecule, you'll see it goes over that. So this has 26 electrons. So let's write the correct structure on the right. So with molecules containing boron, boron is one of the exceptions to the octet rule. So it's actually satisfied even with just 6 valence electrons. So I'll write that down. That boron is an exception to the octet rule. And now if we count out our electrons, we should have 24 in this new structure. Okay, so now moving on to E. Already you can see that something is wrong because the fluorine has a double bond. And typically it's not that common for fluorine to have a double bond. And you'll notice that it has more than a full octet as well, which is unlikely. So I'll just say fluorine has more than 8. And we have 14 here, but let's calculate how much electrons we're supposed to have. So for hydrogen, it has 1 valence electron, oxygen has 6, and fluorine has 7 that participates in the bonding. So if we add it all up, there are 14. So let's try to draw the correct molecule. So instead of fluorine having the double bond, we are going to keep it as a single bond. And just have 2 pairs of lone pairs on the oxygen, and we should still have 14 valence electrons without the fluorine being like oversaturated. Okay, so this is the correct structure. And now let's look at the last molecule. And let's try to see how many lone valence electrons it should have. I don't really know the order that this molecule should be in, but anyways, carbon has 4 valence electrons, hydrogen has 1, oxygen has 6, fluorine has 7. So if we add them all up, we should need 18 valence electrons. So if we look at the incorrect structure, everything seems fine except for the oxygen, which is not satisfied. So let's count out how many electrons are in the molecule. 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So there's still 18. But Instead of the lone pair on the carbon, I'm going to convert it into a bond, another bond with oxygen to have a double bond. And now we should still have 18 electrons, only now the oxygen has a full octet. So this structure is now correct. So let's compare answers with the junior tutor, starting from the first page. So HC double bond N. So the total number of valence electrons in the given Lewis structure is equal to 12. The actual number of valence electrons for HCN is 10. Therefore, the correct structure is the carbon with a triple bond. For B, the total number of valence electrons in the given Lewis structure is equal to 12. The actual number is equal to 10. So valence electrons, therefore, 10 valence electrons. So therefore, the correct Lewis structure is the triple bonded carbon. Next, the octet rule is not satisfied for any of the elements, and the number of valence electrons for this structure is equal to 12. Actual number of valence electrons is equal to 16. Therefore, the correct Lewis structure is just contains double bonds instead of single bonds. For D, this Lewis structure has a total of 26 valence electrons. Actual number is 24. Boron is an exception to the octet rule. It is satisfied with having 6 shared electrons. Therefore, the correct Lewis structure has the boron without containing an extra lone pair. So for E, this Lewis structure has the correct number of valence electrons, 14, but the fluorine atom has more than 8 shared electrons. Fluorine is in period 2, so it cannot be hypervalent. Therefore, the correct Lewis structure is... So by hypervalent, these can be elements that can have more than 8 shared electrons. So they're usually found in the transition metals. And then lastly, F, the number of valence electrons for this Lewis structure is correct, 18. But the octet rule for the oxygen atom is not satisfied, and it only has 6 valence electrons. The correct Lewis structure is the following, that has now a double bonded oxygen. So this solution is correct. Okay, so now we are on to question number 3. What is the Lewis structure for the nitrate ion? So NO3 minus. Include all resonance forms and formal charges. So first, let's calculate the total valence electrons in the NO3 minus ion. So nitrogen atom contains 5 valence electrons. Each oxygen atom contains 6, and there are 3 of them, 18. And notice we also have a negative charge on the entire molecule, so I'm going to add an extra electron. And then if we add this all up, we should get 24. So now let's draw nitrogen as our central atom. And we'll show all the oxygens. Okay, so now I will fill in all of the electrons. And before I fill out the last one, let's count out how many I've drawn so far. So we have 8, 9, 10. If we recall that each bond contains 2 electrons, I have so far drawn 10 electrons and I need 24. So notice that nitrogen doesn't have a full octet yet, so I'm going to draw a double bond and fill it out. And now let's count out how many electrons are here. So 16, 17, 18, 19, 20, 21, 22, 23, 24. So I have 24 electrons, so all of them have been drawn. And now let's show the charges. So the nitrogen has a positive charge, which makes sense since it is the least electronegative. And the 2 oxygens, which are more electronegative, are more likely to carry the negative charges. So since one of the negative charges is kind of cancelled out with the positive charge, this overall molecule has a -1 charge, which is good, which is expected. So this is one resonance structure of NO3-, so we can draw another one with a different oxygen having the double bond. Just showing all of the electrons still as well. So now these 2 oxygens have a negative charge. And lastly, we can have the rightmost oxygen having the double bond, and the other 2 are singly bonded. Like so. So now I will do a sample calculation for formal charge. So let's try to fit it up here. So the equation for formal charge is the number of valence electrons minus the number of non-bonding electrons minus the number of bonding electrons divided by 2. This is the equation for formal charge. So I'll do the one on the most left, and I'll label all of the different atoms. So since these 2 oxygens are the same, I'll just label the 1. Oxygen 1 and 2. So for oxygen 1, which is one of the single bonded oxygens, we are to calculate its formal charge. We already know that it is -1 because I've drawn it in, but let's say we didn't know. This is how you would calculate for it. So for oxygen 1, it has 6 valence electrons. For the number of non-bonding electrons, these are the lone pairs. So it has 6 non-bonding electrons, and the electrons participating in the bond is 2, and this number is divided by 2. So that's how oxygen 1 has a -1 charge. Now let's do the same thing for oxygen 2. It also contains 6 valence electrons, The number of non-bonding electrons is only 4. And the number of electrons participating in the bond is 1, 2, 3, 4. So 4 divided by 2, which is 2. So this oxygen has a formal charge of 0. Now let's do it for the nitrogen. Nitrogen has 5 valence electrons. It has no lone pairs, so for non-bonding electrons I'm going to write 0. And the number of electrons that are participating in the bond, so there's 4 bonds. So there are 8 bonding electrons. And this is how the nitrogen has a +1 formal charge. Okay, so now let's see what the junior tutor said. NO3-. The number of valence electrons is equal to 5 plus 18 plus 1, which is equal to 24. The least electronegative is the nitrogen atom, so that's the one that will carry the positive charge. And you can see the 3 different resonance structures. Formal charge is equal to number of valence electrons minus number of non-bonding electrons minus number of shared electrons divided by 2. Okay, so this solution is correct. Okay, so question number 4. Which of the following Lewis structures represents the actual Lewis structure for boron trifluoride? BF3. So first let's find out the total valence electrons for this molecule. So boron has 3 valence electrons, and each fluorine atom contains 7. But there are 3 fluorine atoms, so let's multiply this by 3. So this gives us a total of 24 valence electrons. So our central atom is boron. And I'm just going to draw all the terminal atoms attached with a single bond. And I'll show all of the lone pairs on each atom. Okay, so now let's count out how many electrons I've drawn so far. So each bond contains 2 shared electrons, so there are 6 as bonds. So I have drawn 24 in total. And you may notice that boron doesn't have a full octet, but this is okay because boron is one of the exceptions to the octet rule. So I'll just write this down. And it's pretty satisfied only having 6 shared electrons. So boron is an exception to the octet rule. So we don't need to put an extra lone pair on it as well. So if we look at the options the question gives us, it would be the last option as the correct answer. Therefore, last option. Okay, so let's see what the junior tutor said. The number of valence electrons in BF3 is 3 plus 21, which is 24. Boron is the least electronegative atom, so it will be the central atom. Fluorine has 7 valence electrons, so it just needs 1 electron in order to fulfill the octet rule. Boron is an exception to the octet rule. It can be satisfied with just sharing 6 electrons. Therefore, the correct Lewis structure for BF3 is the following. Yep, so this solution is correct. Okay, so question 5. What is the Lewis structure of ozone? So this is O3. Include all resonance forms and formal charges. So let's calculate the total valence electrons. We have the oxygen atom only, which has 6 valence electrons, and we have 3. So we have a total of 18. So the easiest way is to draw them all in a line. And so each bond contains 2 shared electrons. So I've drawn only 4 so far. So now let's try to fill in all of the lone pairs. Okay, so now notice that the central oxygen doesn't have a full octet. So I'm going to bring one of the electrons down from one of the terminal oxygens. And now let's look at what we have. All of the oxygens have a full octet. And to calculate the formal charge, I'll first label the oxygens as oxygen 1, oxygen 2, and oxygen 3. So the equation for formal charge is equal to the number of valence electrons minus the number of non-bonding electrons. So I'll just say NB electrons minus the number of bonding electrons divided by 2. So first let's calculate the formal charge of oxygen 1. So I'll just denote it as O1. So oxygen has 6 valence electrons, and the number of non-bonding electrons on oxygen 1 is 4. And then the number of bonding electrons is also 4, but we divide this by 2. So 6 minus 4 minus 2 is equal to 0. So the first oxygen doesn't have a charge. Now let's calculate formal charge of oxygen 2, which still has 6 valence electrons. The number of non-bonding electrons, however, is now 2. And the number of bonding electrons, so there are 3 bonds, so 6 bonding electrons divided by 2. So 6 minus 2 is 4, minus 3 is positive 1. So the oxygen in the middle will have a positive charge. So I'll just erase these for now. And now let's look at the last oxygen. Oxygen 3 has 6 valence electrons. This time the number of non-bonding electrons is 6. And the number of bonding electrons is 2 divided by 2. So the last oxygen has a formal charge of -1. And we get the following as one of the first Lewis structures of this molecule. So if we were to draw the second one, let's make it so the left oxygen now has the double bond, and the right one, or the single bond, and the right one now contains the double bond. So this is one of the resonance structures of O3 as well. The central oxygen still has a positive charge, and the single bonded oxygen now has the negative charge. And these are the two resonance structures, and how to calculate formal charge. So the junior tutor said that for ozone, the number of electrons, valence electrons, is 18. And they drew the two resonance forms. Yep. And they showed the equation for formal charge, which is the number of valence electrons minus the number of non-bonding electrons minus half of the number of shared electrons. So this solution is correct. Okay, so question 6. What is the Lewis structure? Oxygen difluoride. So let's first find the total valence electrons in the molecule. So the oxygen atom contains 6 valence electrons, and a fluorine atom contains 7, and there are 2 of them. So 14 plus 6 is 20. So now I'll draw my central atom, which is the oxygen, and the fluorines as the 2 terminal atoms. And I'll show all of the lone pairs. So fluorine has 3 lone pairs. And notice that oxygen doesn't have a full octet yet. And we've only drawn 16 electrons so far. So we need 4 more, so I'm just going to draw them in the form of lone pairs on the oxygen atom. So we can draw this showing how the molecule is like bent. And this is the Lewis structure for oxygen difluoride. And the junior tutor said that Lewis dot structure is a representation of an atom, ion, or compound that shows how the valence electrons of the atoms are distributed as bonds, lone pairs, and sometimes radicals. The octet rule can be used as a guideline in many but not all cases, and in drawing the Lewis structures. This rule states that the atom desires to have 8 valence electrons. This can be done via accepting, donating, or sharing electrons. We can apply the octet rule to the atoms in OF2 to determine the molecule's Lewis structure. Oxygen has 6, and therefore to achieve the octet state, it may create 2 covalent bonds. This would require 2 of its valence electrons, so the remaining 4 electrons will be represented as 2 lone pairs. On the other hand, fluorine has 7, thus it needs 1 bond only, and the remaining 6 electrons will be drawn as 3 lone pairs. Based on these, the 2 fluorine atoms must be singly bonded to the oxygen. This way, all atoms achieve the much desired octet state. Thus, the Lewis structure is... Yep. So, this solution is correct. Okay, so question 7. The Lewis structure for carbon disulfide is shown below. What are its electron pair geometry and molecular geometry around the central atom? So let's draw the carbon that has 2 double bonds to 2 sulfur atoms. And the central atom is carbon. So I'll take note of how many lone pairs it has and how many bonding pairs it has. So carbon has 0 lone pairs. And by bonding pairs, it means the 2 sulfur atoms. So 2 bonding pairs. So now let's look up what type of Vesper shape it would have. Oh, I think yeah, VSEPR. Okay, so like a nice chart. So these charts are usually given in the question or like during your test, like in one of the back pages. So the number of lone pairs is 0, and the number of bonds or bonding pairs, or you can call it charge clouds, is 2. So we have a linear molecular geometry. So instead of bond pairs, I'll also denote it as charge clouds. So some tables might refer to them as that. So therefore, CS2 has a linear geometry. And it also has sp hybridization. So I can show that with another table that might show everything. Sounds nice, but it's just like small. Yeah, so this is one of the good tables that shows almost like everything. They show the bond angles, and they also show what type of hybridization it is. So it's pretty small. Okay, here we go. Yeah, so again, we have a generic formula, AX2. The picture looks like kind of like linear. So 2 bonded atoms, 0 lone pairs, and sp hybridization. And they even have the bond angle, which is around 180 degrees. I'm going to write that down as well. Okay, so this is the Vesper theory, which kind of estimates the type of shape a molecule may have. And let's see what the junior tutor said. Oh, they had their own table here too. Hybridization occurs to ensure that the resulting molecule is stable. That is done by minimizing the repulsion between the electron groups, so bonding groups and the non-bonding electrons. As a consequence of this, molecules have to conform to a specific shape that maximizes the distance between the electron groups. Generally, the number of hybrid orbitals depends on the number of electron groups present. For instance, if an atom has 5 electron groups surrounding it, it needs to hybridize 1s, 3p, and 1d orbitals. This yields 5 degenerate, equal in energy, sp3d hybrid orbitals. And to maximize the distance between the electron groups, the shape should be a trigonal bipyramidal. So this is shown like here. And before we proceed to the problem, let us first differentiate what electron or molecular geometry is. Electron geometry refers to the shape when all the electron groups are included, both bonding groups and lone pairs. Meanwhile, molecular geometry considers the shape of all the bonding groups only. The 6 commonly tackled hybridization are shown below with the shapes associated with these. Possible molecular geometries of each hybridization are also provided. Okay, so this is a nice graph that they have, or table. And you can see the linear geometry that we have. And then based on the Lewis structure, there are 2 electron groups in carbon disulfide, 2 bonding groups, and 0 non-bonding. If the number of non-bonding groups is 0, the electron geometry and molecular geometry will be the same. Referring to the table above, since there are 2 electron groups, it must be sp hybridized, and its electron and molecular geometry must be linear. Yep. So this solution is correct. It was very well explained and in depth. Okay, so question 8. What are the Lewis structure and molecular geometry of dihydrogen sulfide? So first, let's find out the total valence electrons in this molecule. For hydrogen, there is 1, and we have 2 of them. And for sulfur, there are 6. So this gives us 8 total. So let's draw the sulfur in the middle and 2 single bonded hydrogens. And we still need 4 more electrons. So let's draw them as lone pairs on the sulfur. And we have the following Lewis structure. So let's look at the Lewis structure, and you'll notice that the central atom, which is sulfur, has 2 lone pairs. So 2 lone pairs and 2 bonding groups, or you can call them charge clouds. So 2 bonding pairs or charge clouds. And now let's look at this handy Vesper Theory table and compare our structure with it. So we have 2 lone pairs and 2 bonded atoms, so you can see it down here. Its molecular shape is bent, and the electron geometry is a tetrahedral. So let me draw how this molecule is bent with the 2 lone pairs like that. Bent and tetrahedral. And you'll notice that it is sp3 hybridized. Okay, so let's see what the junior tutor said. Hybridization occurs to ensure that the resulting molecule is stable. That is done by minimizing the repulsion between the electron groups. As a consequence, molecules have to conform to a specific shape that maximizes the distance between the electron groups. Okay, so they give an example of how to do that, and they differentiate between electron and molecular geometry. So electron is the shape when all the electron groups are included, and molecular considers the shape of all the bonding groups only. So this is why we have both bent and tetrahedral. The bent shows how the 2 hydrogens are bent, and tetrahedral shows how all of the electron groups, like even the lone pairs, are involved, and they can form a tetrahedral shape. Okay, so they have their table. And they also draw out the Lewis structure. And then they see that it is sp3 hybridized and its molecular geometry must be bent. Okay, so this solution is correct. Is bent. And then I'll add the electron geometry as well. Okay, so question 9. Draw the Lewis structure of chlorine trifluoride. So the total valence electrons in this molecule has a chlorine, which has 7, and a fluorine, which also has 7, but there are 3 of them. So this gives us a total of 28. So let's draw the chlorine as our central atom, and the 3 fluorines that are singly bonded. And if we were to count all the electrons I've drawn so far, with each bond containing 2 shared electrons, I've drawn 24 so far. So for the remaining 4, I'll add them as lone pairs on the chlorine to get the following Lewis structure. The junior tutor said that when writing Lewis structures, the total number of electrons that need to be distributed is counted first by adding the valence electrons of each individual atom. If a formal charge is present on the molecule, this is also taken into account in the total number of electrons. A skeletal structure is written first by distributing bonding electron pairs, then they're distributed until the octet is completed. Okay, so they explain pretty well and have the following Lewis structure, which is correct. Okay, so this solution is correct. Okay, so question 10. Draw the Lewis structure for chlorate, which is Cl O3-. For this structure, give each atom an octet, but do not include a formal charge. Okay? So first, let's calculate the total valence electrons we should have in this molecule. So chlorine has 7, oxygen has 6, and there are 3 oxygen atoms, which gives us 18. And we also have an extra electron, and this is from the negative charge of the entire ion. So if we add this all up, we have a total of 26 valence electrons. So now let's draw the chlorine as our central atom, and we'll draw the 3 oxygens around it. And now let's draw in all of the electrons. So notice that our chlorine doesn't have a full octet yet. So instead of a lone pair on this oxygen, I'm going to draw a double bond. And now let's count out the electrons. We have 1, 2, 3, 4, 5, 6. So 12, 13, 14, 15, 16, 17, 18, 19, 20. So we still don't have enough electrons written down. So let me try to draw another double bond. And you'll notice this is how the chlorate ion has its negative charge. And then if we were to count it all out, we would now have 26 electrons in this structure. Okay, so let's see what the junior tutor said. First, determine the total of valence electrons, which is 26. And they showed how, how chlorine would have an extra lone pair as well. And they show the negative charge that the atom would have, or the ion would have. Okay, yep, so this is now 26 valence electrons, so this solution is correct. Okay, let's quickly do question number 11. Draw the Lewis structure of SF2. What is the hybridization? Is it polar or nonpolar? Identify the geometry, and what is the approximate bond angle? So the total valence electrons is 6 for sulfur, and for fluorine it's 7. So 7 times 2, which is 14. So adding it all up, we have 20 electrons in total. So let's draw sulfur in the middle with the 2 fluorine atoms as the terminals. And we'll draw in all the lone pairs. So far, I've drawn 16 electrons if each bond contains 2 bonding electrons. And sulfur doesn't have a full octet yet, so I need to draw the last 4 on sulfur. So this is the Lewis structure. And to find out the rest of the questions, we'll first analyze the molecule. We have 2 lone pairs, and we have 2 bonding pairs, which are the 2 fluorine atoms on the central molecule. So this means that our hybridization is sp3 hybridized. Is the molecule polar or nonpolar? So fluorine is more electronegative than sulfur. So there are dipole moments that occur in the direction of the fluorine atoms. And also the fact that it has the 2 lone pairs shows that they don't cancel each other out. So therefore, this molecule is polar. And to identify the molecular geometry, we'll use this Vesper table. So 2 lone pairs and 2 bonding atoms gives us the sp3, and we have a bent molecular shape and tetrahedral electron geometry. So I'll just write both down. And the approximate bond angle is around 109.5. Also using this table. Okay, so let's quickly see what the junior tutor said. They have the following Lewis structure, which is correct. sp3 hybridized. Since it's not symmetrical due to the lone pairs and the bonded atoms, it's polar. Has a bent molecular geometry and a bond angle of approximately 109.5 degrees. So this solution is correct. Now let's quickly do one more question, which is just to draw the Lewis structure of boron trichloride. So boron has 3 valence electrons, and chlorine has 7, and there are 3 chlorine atoms, so we have 24 electrons in total. So let's draw the boron as our central atom, and just the 3 fluorines around it. And we'll show all of the lone pairs. And if we remember that each bond contains 2 shared electrons, if we count out the total number that I've drawn so far, we have 24, which is what we want. And notice that boron doesn't have a full octet, but this is okay since boron is an exception to the octet rule. So it is perfectly stable with only the 6 shared electrons. And let's see what the junior tutor said. Drawing Lewis structures, the total number of electrons should be counted first. Formal charges are added, and they have the following Lewis structure. So 24, 6 are 3, remaining 18. Yep, so this solution is correct. Okay, so those are all the questions for today's session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also, if you liked today's video, go ahead and give it a thumbs up and comment. And you can share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.